We're going to talk about interpolation and spatial transformations of images. So we often need to estimate or interpolate the value of an image at a non-integer location. So if we know the values of an image at these integer locations, basically f row 2, column 1, f row, or I'm sorry, x2, y1, x3, y1, etc. But if we were to try to, let's say, expand the image, we might want to calculate values such as points at non-integer locations such as 2.5, 2.5. So how do we do that? We can do that by, the easiest way would be just take the nearest neighbor. So in this case, if it's exactly equal, we could just take one of the 4 nearest neighbors. If it's not, we just take the closest one. A better way is to interpolate using a bilinear equation. So we take a combination of the 4 closest neighbors, basically the 4 surrounding this. Even better would be a bicubic function which uses the 16 closest neighbors. This is more computationally expensive but gives the best results. So I mentioned resizing an image. This is a image where the values are known at the blue dots. Our output image is twice as big, so we need to calculate these additional values here. So we need to assign values to each pixel in this output image. The best way to do that is to actually start with the output image. We scan through the output image point by point, and then we figure out where in the input image that value should be coming from. And if the value comes from a non-integer location, such as here, we go ahead and interpolate what the value should be. So mathematically speaking, we have 2 images, I1 and I2. Let's say the coordinates system for I1 is V and W, and for I2 it's X and Y. So if we are doing a simple scaling, then we can calculate a scaling factor Cx for the horizontal and Cy for the vertical direction. But since we're actually going to scan through the output image I2, and we need to calculate where the values are in I1, I need an equation that gives me V and W in terms of X and Y. So that's the inverse function that I want here. Here's a simple program in Matlab that does nearest neighbor interpolation for resizing an image. So here I'm reading in an image. The size is M1 by N1. I'm going to pick the size of my output image, M2 and N2, and then here I'm calculating the scaling factors Cx and Cy. Then I go through with 2 for loops and calculate for each point in the output image, xy, where that came from in the input image. So this is just doing a nearest neighbor interpolation, so it's going to round off these values to the nearest integer, and that's the value it's going to assign. So let me go ahead and copy that. Here's Matlab. Okay. Okay, so I'll go run this program that I just entered. And this is going to read in the cameraman image, which is 256 by 256, and scale it to 300 by 100. So that's the input image I1 and the output image I2. And just to display those, okay. All right, let's look now at a little bit better way to do interpolation. So we can do bilinear interpolation using a bilinear equation such as this. So we need to calculate 4 coefficients a, b, c, d, and then we can calculate the value at our the point that we're trying to interpolate as f of x, y. This is equivalent to doing linear interpolation in one dimension and then the other. So here's an example. Let's say we know the values of the image at the Q points. There's 4 of those, and we want to find it at P here. So first we're going to interpolate horizontally to find the values R1 and R2. And we can do that fairly easy with these equations, which are simply doing a linear interpolation from here to here. Once we have that, we can interpolate vertically. So we have R1, R2, and we can interpolate this way to find f of p. So if we assume that the values of q are at the corners 0, 0, 0, 1, 1, 0, and 1, 1, we can always translate our coordinates so that this is the origin. Then this equation simplifies to this. Okay, so this is our bilinear equation that we can use to calculate f of x, y.